I was telling Adrian this, but Fazel is actually the first person I've ever met in condensed matter research. Fazel did his PhD in the University of Toronto, and then he did one postdoc in Sherbrooke with Louis Taillefer, and then he did another postdoc in chemistry with Bob Cava at Princeton. And since 2016, he's a professor at Boston College, and Fazel is an expert in material growth, chemistry, understanding the physics of complex materials. So I think we are in for a great talk today. Fazel, the floor is yours.
Thank you. Thanks, Alberto, for the kind introduction and for the invitation. And also thanks to Adrian for helping us set up this presentation. All right, so I'm going to, let me just get this here for a second. All right, so I'm going to talk about possibly two topics if I can. If not, I'll finish one of them. And I believe we are on Zoom. Hopefully people can also stop me if they want to and ask questions. All right, so I start with the acknowledgements. The research that I'm going to present and everything I've done in the past couple of years has benefited immensely from collaborations with national labs, both within US and abroad. I would also like to thank the academic collaboration with various academic institutions. We have been collaborating with Alberto when he was in Brown, and I look forward to continuing and expanding those collaborations now that he's at Northeastern. And since I can't use maybe my pointer, I'll try to go through the online pointer. This. So my lab is focused on quantum materials. We make a variety of materials. When the interest in my lab is quite broad. We work on quantum spin liquid materials, which is what I'm going to talk about today for the most part. We work on polaronic metals with extreme magneto-resistance, systems with positive or negative magneto transport response. We work on topological superconductors, chiral crystals, van der Waals crystals, Kagome flat band systems. So the research is fairly diverse. But for today's talk, I'm gonna focus on two problems and kind of discuss some of the insights that chemistry brings to these physics problems. The first one is a problem of quantum spin liquids. Particularly, I will focus on Kitaev materials or the Kitaev model of spin liquid and discuss the role that intercalation chemistry has played in this research over the maybe past couple of years. And I'll give you examples from 5D, 4D, and 3D systems. And if time allows, there's another topic I would like to talk about, and that's topological magnetism. And there I'll discuss the role of Weyl electrons, these relativistic quasi-particles, that in driving magnetism, not in the sense that they exist in a magnetic material, but I'd like to show or convince you that Weyl electrons could actually drive magnetic textures. So we'll see how far I go. I start with the quantum spin liquid. Again, feel free to stop me at any time and ask questions. I'll try to monitor the chat as well. All right. So the Kitaev model of spin liquid was introduced back in 2006. It is a model that describes spin-spin interactions on a honeycomb lattice in 2 dimensions. And the interactions are very specific. They are bond directionals in the sense that if you are on a honeycomb lattice and you have 3 nearest neighboring bonds, only one component of spin is allowed to interact along each bond. For example, X component on these blue bonds, Y components on the green bonds, and Z components on the red bonds. And such a model is massively frustrated. It leads to a quantum spin liquid ground state. And in that state, you can have fractionalization of spin or electrons into Majorana degrees of freedom. So there has been plenty of interest in basically realizing that model. And the realization of that model in terms of materials started by pivotal theoretical work, in fact, by Jakeli and Khalilin back in early 2010s, where they proposed that 5D iridium oxide materials with a honeycomb lattice, namely lithium iridate and sodium iridate, could be the realization of this model. In these materials, you have iridium atoms on the vertices of the honeycomb lattice. Lithium atom sits at the center of the honeycomb. And because of the strong spin-orbit coupling of iridium, there is hope for bond directional anisotropic magnetic interactions due to strong spin-orbit coupling. And also, the model, the Kitaev model, is a model for spin-half particles. Here, also, you can have a spin-half, not in the sense that you have S equal half, but you will have a J equal half. Total angular momentum, J, which is the sum of L and S, could be 1/2. And the way that that works is because of the special crystal field and filling of the 5D orbitals in iridium. Basically, the 5D orbitals under an octahedral crystal field split into T2G and EG manifolds, and then the T2G manifold under spin-orbit coupling splits into J effective 3/2 and 1/2. And then when you put the 5 electrons in those levels, you end up with a single electron in the J effective half. And so this is a J equal half model on a honeycomb lattice with strong spin-orbit coupling. So those are the initial ingredients for possibly a Kitaev system. The materials were synthesized again back in 2010s and studied intensely ever since. And the main sort of takeaway from this research is that these materials are relevant to the Kitaev model, but their ground state is not exactly as equal, in the sense that these systems order magnetically at around 15 Kelvin. But if you look at the high temperature tail of magnetic susceptibility and you fit it to a Curie-Weiss law, you would see that the so-called Curie-Weiss temperature, which is proportional to the exchange coupling, is of the order of hundreds of Kelvin, whereas the magnetic ordering temperature is about 10 to 15 Kelvin. And therefore, these systems are indeed frustrated. However, they still order magnetically at low temperatures, so they're not exactly in the spin, sort of Kitaev spin liquid ground state, but they're close to it. Now later, it was realized theoretically that because these systems, of course, are frustrated but also order magnetically, you need at least basically two, you can describe their Hamiltonian with two terms. The first one would be the Kitaev term, which drives frustration. The second term is the Heisenberg interaction, which leads to magnetic ordering. But it's also been realized theoretically that there are other terms that look like a Kitaev term, but somewhat different. We call them off-diagonal exchange terms. These terms are also very important in that they determine the type of magnetic ordering or the specific texture of magnetic ordering in these materials. And therefore, in fact, this extended Kitaev-Heisenberg model has become a fruitful theoretical platform in that by tuning the relative strength of K, J, gamma, and gamma prime, you can map out a rich phase diagram of magnetic phases. Now, roughly speaking, these different exchange couplings, K, J, gamma, and gamma prime, roughly speaking, they're tuned by the bond angle between iridium, oxygen, and iridium in the lattice structure. They are super exchange or direct exchange interactions, and therefore the relative strength of these interactions depends on, to some extent, depends on the geometry of the lattice, namely the bond angle or bond distances between iridiums and the ligands. If I want to really simplify this, the Kitaev model is predominantly a super exchange interaction. It is an interaction between the YZ orbitals and PZ orbitals of oxygen and iridium. Then the Heisenberg interaction turns out to be predominantly a direct exchange interaction between, let's say, the XY orbitals. And this gamma and gamma prime, the off-diagonal exchange interactions, are a combination of these two. Now, therefore, as I said, by tuning the lattice parameters and the bond angles and bond lengths, you have a hope of tuning these relative, the relative strength of these coupling constants. And this can be done theoretically and you can basically construct complex phase diagrams. We call these global phase diagrams because the way that basically the parameters in the phase diagram are encoded in angles on a sphere, theta and phi. And these angles basically give you the relative strength of J, K, and gamma in the way that I have written in the simplest possible way in this slide. Now, the mapping of phase diagram is an ongoing effort. There are multiple phase diagrams by different groups. They all consider maybe slightly different terms in the Hamiltonian. For example, gamma prime is not included here. You can include it. You can do this in 2D honeycomb lattices, but you can also do it in 3D hyper honeycomb lattices. And as I said, this has been an extremely fruitful theoretical research area. But experimentally, it has been a challenging area, and mainly due to the lack of materials that correspond to this physics. I only showed you two of them: lithium iridate and sodium iridate. There's another system which is a 4D transition metal halide, is ruthenium chloride. That's also a very good candidate for this physics, but there are not many more materials really. The phases that you see on this phase diagram are, for example, simple ferromagnetic phase. You can see antiferromagnetic phase, or what we call 120 degrees vortex-like antiferromagnetic phase. That's the green region here. You can have these stripy or zigzag phases, which are shown in pink color and orange color here. And the gray color here, that's an incommensurate spiral order. As I said, there are plenty of different magnetic phases on this phase diagram, but experimentally, so far there are at least these three materials are the main materials that have been studied in relation to this physics. And I put some stars for, roughly speaking, where they lie on the phase diagram. Now, the contribution from my group to this research has been to basically open a chemistry way to create new materials that could become more stars on this phase diagram. We've been trying to put more materials on the map. And we've done it by means of a chemistry technique called topochemical exchange reaction. And I'm going to give you examples of this kind of exchange reaction in 5D, 4D, and 3D systems. I start with the 5D. Now, the idea of a topochemical exchange reaction is that you start with a known template, for example, lithium iridate or sodium iridate. And what you do is that you change some of the cations, usually the cations that are between the layers. And by doing so, you create a new version of it. For example, let's look at the crystal structure of lithium iridate at the bottom. You have honeycomb layers of lithium and iridium that are separated by layers that only contain lithium. And so here at the bottom, you have another honeycomb layer. What we do in such reactions is to take out the lithium atoms and replace them with silver atoms. Now, the top and bottom layers are still honeycomb layers of lithium and iridium, but the middle spacer layer is silver instead of lithium. Now, why is that? Of course, that gives us a new material, in this case, silver lithium iridate. But the reason to do this is not just to make a new material. There's actually something deeper that's happening as a result of this exchange reaction. The important thing that's happening as a result of the exchange reaction is a change in the bond angle. Remember that I explained the sort of relative strength of different coupling, exchange couplings is determined by the orbital overlap between iridium, oxygen, and iridium orbitals. That very much depends on the bond angle. And this bond angle can be tuned by this chemical reaction, because if you look at the crystal structure of lithium iridate, you see that the lithium atoms between the layers are coordinated octahedrally with oxygens. There are 6 oxygens around each lithium. It's an octahedral coordination. But then when you go to the silver version, each silver atom is coordinated by only 2 oxygens, one from top and one from the bottom. Sometimes we refer to this as a dumbbell coordination. Now, in order to go from an octahedral coordination to a dumbbell coordination, the oxygen atoms within the honeycomb layer must move to accommodate the change of coordination between the layers. And in doing so, when the oxygen atoms move slightly to accommodate for the change of coordination between the layers, we are indeed changing the iridium-oxygen-iridium bond angle. And by doing so, we are changing the orbital overlaps, and we change the strength of these different exchange interactions, direct and indirect. And we will change basically the location of the material on the phase diagram, on the so-called global phase diagram of these materials. Now, exactly how that happens and whether we can predict where to go by changing the bond angle is a very complex problem. It requires very careful quantum chemistry calculations. And as of now, there's not, at least there's no really systematic effort to kind of predict exactly which atom you replace with which atom and how you can basically move in this phase diagram. But of course, I'm an experimentalist, and this is, in some sense, a very exciting field for experimentalists to go ahead and try different combinations, and of course, work with the theorists to hopefully, in the long run, develop a predictive model so that eventually we can make our way not to different phases on this phase diagram, but also to the poles of the phase diagram where the spin liquid actually exists. All right, so with that, let me show you some data about one of the new materials we made. This is silver lithium iridate. We made a couple of these systems in the past couple of years, but I start with this one as an example, silver lithium iridate. Now, this work has been led by my former PhD student, Faraz Bahromi, who recently graduated. She's now a postdoc. Okay, so the silver lithium iridate is basically has silver atoms between the honeycomb layers, as I explained in the previous slide. So here I show transmission electron microscopy images of both the parent compound, lithium iridate, and the daughter compound, silver lithium iridate. The crystal structures are shown in the insets. The first thing that you realize in these transmission electron microscope images is if you can look carefully into the image to the left, you'll see patterns of a pair of atoms separated by an empty space. So you have two atoms separated by a pair of, basically a pair of atoms separated by empty space. And this sort of repeating pattern is the transmission electron microscopy signature of honeycomb ordering within the layers. So we see proper honeycomb ordering in the layers of lithium iridate. We also see a very nice stacking of the unit cells on top of each other. So this long line of stacked unit cells shows you that there is a very nice monoclinic stacking. The space group is C2 over N, which is a monoclinic space group. You see a very nice monoclinic stacking of unit cells. However, every now and then you see a stacking fault in the sense that the direction of stacking changes. And of course, that these are layered materials. It is expected for them to have stacking faults. But you see that in the new material we made in silver lithium iridate, the stacking faults are even more prevalent than the parent compound. And the reason for it is because these silver atoms between the layers, they form these double bonds, which are much more fragile or kind of, let's say, less robust than these octahedral coordination of lithium atoms. So the adjacent layers can every now and then twist with respect to each other, and they create this kind of zigzag stacking of the monoclinic unit cells. And that's why the silver lithium iridate has more stacking faults. But the stacking fault is, of course, an extended defect in the lattice, but because the magnetism in these systems is predominantly restricted to the 2D honeycomb layers, this is not necessarily a very bad type of disorder, although it is a type of disorder. The worst kind of disorder that can happen in these systems is if the silver atoms replace the iridium atoms and they disrupt the honeycomb ordering within the layers. And that actually can happen. We have seen this in the first generation of samples that we made. So a lot of chemistry work in my group has been focused on removing these kind of disorder, where basically some silver atoms can include themselves in the honeycomb layers. We call them silver inclusion. And then the material doesn't order magnetically, but it is not because of a proximity to a spin liquid phase. It's because the material has this kind of heavy disorder. So anyways, the point of all this discussion was to tell you that I think there is plenty of room to use electron microscopy, especially in this physics. It's very important to understand the role of disorder, something that I believe has been really not considered properly until now, and we're trying to really push the application of transmission electron microscopy in this field. All right, my group also does other experiments. We do mu-SR experiments, which is a local probe of magnetism. Here I show an example of mu-SR data in silver lithium iridate. In mu-SR, you send a polarized beam of muons. The muons implant in the material, and they decay after 2.2 microseconds into pions. But before they decay, if they are in a magnetic environment, they will perform Larmor precession in the local magnetic field. And as they perform the Larmor precession, they decay into pions. Then those pions will exit the material, and there are detectors that are covering the room where basically the sample is sitting. And therefore, from the asymmetry in the detection of these outgoing pions, you can say something about magnetism in the material. For example, if this asymmetry shows oscillations, you know that the muon was subjected to a local field. It was performing a Larmor precession before it decayed into pions. And from the frequency of these oscillations, you can find the strength of the local field in the material. Also, from the shape of the oscillations, you can say something about the type of magnetic ordering. For example, in this material, we see a distinctly Bessel function shape at low temperature. The red data is at 0.28 Kelvin. The yellow line is a fit to the data. You can see that it's not a sinusoidal oscillation, but it's more of a damped Bessel oscillation. And this tells you that the order is possibly an incommensurate order instead of a commensurate order. Now, without going into more details about mu-SR, I would like to point at one thing in this slide. In this material, you see that the onset of oscillations, which shows long-range order, happens at around 8 Kelvin. And therefore, the magnetic ordering of this material happens at 8 Kelvin. We also collaborated with a group of Takashi Imai at McMaster University on NMR experiments. In NMR, you also see a drop in 1/T1 at around 8 Kelvin. And therefore, the magnetic ordering of this material is at 8 Kelvin. Now, this is silver lithium iridate. The parent compound, lithium iridate, orders at 15 Kelvin. So by performing this exchange reaction, we could reduce the onset of long-range order from 15 Kelvin to about 8 Kelvin. And in some sense, the material has been approaching a quantum spin liquid. It still orders magnetically. The ground state is not a spin liquid, but at least it has a lower transition temperature than its parent compound. So in that sense, it has been a successful experiment. So this is one material, silver lithium iridate. It's as I said, it was a 5D transition metal where we performed the exchange reaction. But we also extended this research to 4D transition metals. And for example, there is a 4D system, lithium rhodate, which also can undergo the same exchange reaction and by removing lithium atoms from between the layers and replacing them with silver, and that leads to a new material, silver lithium rhodate. Now, why do we study the 4D transition metals? Again, there's a sort of a heuristic chemical intuition for that. As I explained previously, the Kitaev interaction is predominantly a super exchange interaction, whereas the Heisenberg interaction, which is responsible for magnetic ordering, is predominantly a direct exchange interaction. Now, when you go from 5D to 4D, both interactions become weaker because the spatial extension of 4D orbitals is less than 5D orbitals. But it so happens that the direct exchange interaction weakens faster than the Kitaev exchange, than the indirect exchange interaction. And as such, although both K and J go down when you go from 5D to 4D, the Heisenberg interaction goes down faster. And therefore, the ratio of Kitaev to Heisenberg interaction actually increases. And it seems like the 4D transition model honeycomb systems are a good place to look for Kitaev spin liquid. And for example, ruthenium chloride is also a very well-known material that has been studied extensively in relation to Kitaev physics, and that is also a 4D transition model. All right. Now, again, the 4D systems are also spin half, just like the 5D systems. So let me explain the motivation behind this experiment that we did. Other than studying a 4D system, we started collecting data on various candidates of Kitaev spin liquid. And here is a phase diagram. The vertical axis is the ordering temperature. The horizontal axis is the so-called Curie-Weiss temperature, which is approximately proportional to the Heisenberg coupling, or J. Now, all the iridates are kind of in the same corner of this phase diagram. They all have TCs of somewhere below 15 Kelvin, and they have Curie-Weiss temperatures of about 100 Kelvin to 150 in the negative direction, which means that they have antiferromagnetic exchange. The different points here show different materials. The materials with lower transition temperature are the ones that we made after exchanging either lithium with silver or with copper or with hydrogen. I didn't show all of those materials, but I showed you one of them, for example, a silver lithium iridate. Yes.
Which one is the pink one, most to the left?
Do you remember? I should remind myself which one that is. If I take a guess, however, I think it may be sodium iridate, but I can let you know. Yeah. Yeah. So I didn't list them here. Sorry, but I can do the list. Yeah. For example, the yellow one here is hydrogen lithium iridate, or the pink one here is the copper iridate. Okay, then you also have ruthenium chloride. This one has a positive Curie-Weiss temperature. That is basically has a ferromagnetic exchange, but in polycrystalline material. It turns out the exchange can be very anisotropic in this system. So all the data I'm showing here is in the polycrystalline samples. Now, here is lithium rhodate, the material that we wanted to exchange and study. And basically, the idea was that when we exchanged the iridate materials, we saw that TC always goes down. And so we wanted to exchange lithium rhodate, which has already a very small TC, and basically bring the TC to zero, if possible, and realize a spin liquid material. But like many good ideas, it actually went quite wrong. So the experiment went totally the opposite direction. When we did the exchange reaction, the material, not only the TC didn't go down, it went up by order of magnitude. And this is clearly was not what we expected. It completely went the opposite direction to what we predicted in the beginning. And it's sort of kind of the fun thing about doing research. Of course, when you predict something and it comes true, that's exciting. But sometimes also when you predict something and it completely goes wrong, that's also very exciting, because it shows that you're going to learn something new. And we learned a lot in that experiment. So what we learned in this experiment was that there is another very important structural parameter that plays a significant role in this physics. And that parameter is the local distortion of octahedral units in these materials, specifically a trigonal distortion. A trigonal distortion happens it can happen in any octahedral coordination when you take, for example, the top 3 atoms in a triangle and press them against the bottom 3 atoms, in this case, oxygens. And therefore, you can trigonally either compress or stretch each octahedral unit. And it so happens that in lithium iridate and silver lithium iridate, you have quite different degree of this trigonal distortion. Lithium, we performed crystallographic analysis of lithium rhodate and silver lithium rhodate, and mapped and basically found all the bond angles between oxygen, rhodium, and oxygen in both compounds. And then we determine something called a bond angle variance, which is basically the variance of the bond angle from the ideal 90 degrees bond angle in an ideal octahedron. And we found that that bond angle variance is about 3 in lithium rhodate, but it is double in silver lithium rhodate, it's 6. Even if you just kind of try to focus on this image at the bottom and then this image on top and toggle between them yourself, just look down and look on top, you will see that the oxygen atoms are actually squashed against the rhodium atom. If you do it a few times for yourself, go down and up between these two images, you'll see that the oxygen atoms are squashed against the rhodium atom. And that is the trigonal compression. All right. Now, what does that do? What that does specifically in the rhodate, in the 4D system, is that it will change the way, it will basically change the filling of orbitals and the character of the orbitals. In short, the trigonal distortion can change the fabric of the spin orbital wave function in the material, and as a result, it changes the physics of the material. So here is how that happens. In lithium rhodate, you have T2G orbitals from rhodium, 4D orbitals, and those T2G orbitals split under spin orbit coupling into J effective 3/2 and 1/2. That's the same thing as in the iridates, and you end up with 1 electron in the J effective half. That's the common scheme for iridates and lithium rhodate. In silver lithium rhodate, however, things change. Here you start with the T2G orbitals, but you have a pretty strong trigonal distortion. So that it induces a new crystal electric field. The trigonal compression induces a new electric field, and it further splits the T2G levels into an A1G and an EG prime. The A1G orbital, which has lower energy, is purely a DZ squared orbital. So then all the weight of the X and Y orbitals goes into that EG prime. Now that EG prime manifold then under spin orbit coupling also splits into 2 levels. And when you put 5 electrons in these 3 levels, you end up with 1 electron in the top level. That electron now is in the top orbital that came from EG prime. Therefore, this electron, even though it's a spin half, so you again get a spin half, but this is a purely spin half state. It doesn't have an orbital angular momentum component. L is 0. You have S equal 1/2. Unlike the top case in lithium rhodate, where you actually have L plus S or J being 1/2. And these two states are quite different. In fact, we can plot them. So anybody could basically draw the d orbitals and superpose them. And you can draw how they look like. So here is the way that the spin half states look like in silver lithium rhodate. Notice that it's a linear combination of d orbitals, but it has no z squared in it. Now you add z squared, right? And then the shape of the spin orbital wave function changes. In fact, you can even see that the spin half wave function in silver lithium rhodate has a kind of a trigonal or a triangular symmetry. This is evidence of that trigonal compression that's happening to the lattice structure and is responsible for this state. Whereas the J effective half state has a cubic symmetry, which is a symmetry of a more perfect octahedral coordination. So in fact, our chemical reaction has led to a change of spin orbital state at an atomic level, which I find quite exciting. Now, this is not, of course, this was a kind of a theoretical discussion of what's happening, but there's also experimental evidence for this. The experimental evidence comes from X-ray absorption spectroscopy, again, something that Alberto knows much better than I. In X-ray absorption spectroscopy, you can do cool things. You can actually determine the strength of spin orbit coupling by measuring the absorption at the rhodium L3 edge and L2 edge, and calculate the ratio of the area under this peak to that peak. This is called a branching ratio, BR. We did this experiment in lithium rhodate. We also did it in silver lithium rhodate. And in both cases, we got the intensity under the rhodium L3H and L2H divide by each other, you get a branching ratio. And notice that the numbers are different between the two materials. There is some proper theoretical treatment of this branching ratio, which I'm not going to go through, but to summarize, the branching ratio will be related to this parameter R, which itself is basically a ratio of expectation value of L dot S, which is the spin orbit coupling operator, divided by the number of holes. In these two materials, you basically have 5 electrons and you have 5 holes. So they're the same in number of holes. If you get the branching ratio, you basically get the expectation value of spin orbit coupling. And what we found was that L dot S is 1.4 in lithium rhodate, but it's 0.3 in silver lithium rhodate. Remember from the previous slide, I said that the orbital angular momentum is quenched in this material. And here you can also see that L dot S is much smaller in this material. Of course, it's not zero. If it was the theoretical picture that I showed you, it should have been zero, but it's not exactly zero because this is the real material, not the calculation. But it indeed looks like L dot S has quenched in this system, in the new material, the silver lithium rhodate. And of course, this happens because of the trigonal distortion, which is small in lithium rhodate, but large in silver lithium rhodate. And therefore, we understand the behavior of these material, which is very different from each other. That change of behavior is due to the change of regime. Lithium rhodate, which orders at around 6 Kelvin, is in a regime where spin orbit coupling is much stronger than the trigonal distortion. But the silver lithium rhodate is in the opposite regime. It's in the regime where the trigonal distortion is much smaller, is much stronger than the spin orbit coupling, and therefore the spin orbital wave function is completely changed from J effective half to spin half. Okay, so that basically explains this change of behavior between the two materials. The state that silver lithium rhodate is in has a very strong Ising anisotropy as well, which does not exist in lithium rhodate. So totally different regimes. Now we did this. How much more time do I have? How am I doing?
50.
Okay, sounds 15.
All
right. Now, so this was of course an experiment. You can call it a chemical pressure experiment or some kind of a chemical experiment where we change the behavior of the material by changing the atoms from between the layers. But now what we ended up having was a material with a very, very high, with a relatively high antiferromagnetic transition at around 100 Kelvin. So in the next or the latest project, we decided to get this material and pressurize it and see what happens, because pressure is another tuning parameter, and see if we can tune back this material to where it came from, if it is possible or not. This was, again, just the idea behind the experiment. Not everything goes exactly the way you think they go. But in this case, indeed, what we predicted actually happened, in the sense that we started with silver lithium rhodate. It has a transition temperature of about 100 Kelvin. We pressurized it. And in relatively low pressures, about, let's say, 3 to 4 GPa, the magnetic transition temperature went down pretty quickly. The rate of suppression of the transition temperature is 20 Kelvin per GPa. It's among the fastest suppression of the magnetic transition that I'm aware of, extremely quick, actually. And in fact, when we're doing this experiment, when we were up to about 1 or 2 GPa, we originally thought that we can basically press Tn all the way to 0, by about 4 to 5 GPa. And I'll show you what happened. So let me explain the data. So the experiments here are done basically in collaboration with a group of Alex Serlin and Philip Gegenwart. Basically, we pressurize these materials. There is a peak in the magnetic susceptibility of the sample. That peak shows the magnetic transition temperature. At zero pressure, it's at about 100 Kelvin. But when we increase the pressure, this magnetic transition temperature is suppressed to lower temperatures. And those are basically the data points you see here. As you increase the pressure, Tn goes down. Then we performed a Curie-Weiss fit to the data. And from the Curie-Weiss fit, we got two information. One information is the Curie-Weiss temperature. That's called theta Curie-Weiss. And that is shown as blue squares. The important observation is that the Curie-Weiss temperature and the transition temperature are suppressed together in parallel. Now, the Curie-Weiss temperature is proportional to Heisenberg coupling. This basically tells you that Tn is going down because Heisenberg coupling is going down. Of course, these materials, remember, they have at least two interactions. There's Heisenberg and there's Kitaev. So the fact that Heisenberg coupling is going down is a promising observation in the sense that you would hope that the ratio of Heisenberg to Kitaev interaction goes down, or other way around, the ratio of Kitaev to Heisenberg goes up, which is what we really like to have. The second information that comes from this Curie-Weiss fit is the effective moment. And we saw that the effective moment remains unchanged under pressure. And that's also a very important observation, because that tells us that although the magnetic transition temperature is being suppressed, the actual magnetic moment is not going anywhere. The system is still in the spin-half state. But the balance between Kitaev and Heisenberg interactions is changing in favor of potentially Kitaev interaction as transition temperature is going down. Indeed, there are other systems where kind of similar to this. For example, there's a hyper honeycomb beta lithium iridate where you pressurize it and it goes from magnetic to non-magnetic. But in that system, the effective moment also goes to zero. And the reason why it goes to zero is because structurally that system undergoes a structural transition. It goes from a honeycomb lattice to a dimerized honeycomb lattice. And when you form dimerization, the magnetic moment of every single iridium, which is basically spin half, will be dimerized. You now form these iridium-2 molecules, quote unquote, and they have no magnetic moment. So basically you lose magnetic moment and therefore the system is non-magnetic, but that's not really exciting. Here, that is not happening. You have the spin halves and transition temperature goes down. Now, at higher pressures, this is the susceptibility data at higher pressures. So this peak goes down with pressure, but at higher pressures, we kind of lose the peak altogether. You may see a little bit of it still at about 4 GPa. That's why basically our data ends here, because we cannot measure at higher pressure. Unfortunately, it's a technological problem. But basically, we lose the transition apparently at these pressures. And exactly how these points are going to approach, let's say, zero is not very clear at this moment, because this is the maximum pressure we could go to experimentally. And nevertheless, it's a very promising result in that transition temperature is being suppressed, magnetic transition is kind of lost, there's no peak at higher pressures, and so it seems like we kind of suppressed at least the Heisenberg interaction without any structural changes. And that is a very important part of the story. We performed X-ray measurements under pressure in diamond anvil cells, and we found that up to about 6 gigapascal, which is well beyond this phase diagram. So this is 5 GPa, 6 GPa would be here. So it's well beyond all of this. Up to those pressures, there is no structural transition in the system. Almost any other honeycomb lattice that you pressurize at about maybe 2 GPa or so, you have a dimerization. So far, at least anyone that I know of, beyond 2 GPa, you have a dimerization. So it's very hard to tune this kind of Kitaev interaction and Heisenberg interaction with pressure, because before you can get something interesting, the structure changes. But here we were extremely lucky that in silver lithium rhodate, the structural change did not happen actually. Eventually at higher pressure, there is a structural transition, and it happens at about 6, as I showed here, at about 6.6 GPa, where you can see that this peak splits into 2. And that is indeed a dimerization transition, but that happens at much higher pressures.
What is the jump? I mean, I'm sure you get this question a lot. But in the previous slide, one more. What's that jump around 150K in the green curve?
Oh yeah, good question. Yes. So this is not an issue of experiment. So basically, so it's not due to the material; it's due to the pressure cell. So when we do these experiments, you get the data, the susceptibility data, has the susceptibility data from the sample as well as the susceptibility data from the cell, which is paramagnetic, the pressure cell itself. But we need to subtract the pressure cell susceptibility. It's a paramagnetic susceptibility. It's boring, but you have to subtract it anyways. And it is that subtraction that usually the subtraction is such that near horizontal zero, right? You get oftentimes you get a jump in the data because that's basically when you go through this subtraction, you'll see that near zero value there's a jump usually. But it's just due to the fact that we're subtracting the pressure cell.
All right. Thank you.
Contribution. Yeah, doesn't come from the sample. Doesn't come from the material. Yeah, very good question out there. Especially for theorists to notice as something is very good that, especially you will see that in the data. It's somewhat of a subtle, in fact, point. Okay. Yeah, so we also perform these experiments at lower temperatures, and again, same thing. We saw that this structural transition doesn't happen until 6 GPa. And just some pictures of the beamline. These experiments were done at a high-pressure collaborative access team beamline 16 BMD in collaboration with Daniel Haskell, who has been a very close collaborator on this research with me over the past couple of years. And so that's basically, this is, here is where you put the beam comes from here, you put your pressure cell here, and this is your detector basically. And in this screen here, you can see inside the diamond angle cell. All right, now I showed you some examples from, so here's again, so just a new material, silver lithium rhodide is another material added to this phase diagram. We believe that it has a stripy order, but it's a longer story, I won't go into it. So I showed you some example of 5D transition metals with this exchange interaction. 4D transition metal, that was the lithium rhodide. So 5D was iridate, 4D was the rhodide system. But I can also tell you a little bit about 3D systems. We also did some work on 3D transition metals. And our interest in 3D transition metal came partly from some work that already was done on, especially on cobalt-based systems. So cobalt 2+ and nickel 3+ are in the 3D7 state. And in fact, theoretically, it's shown that there could be also Kitaev interactions in this 3D7 configuration. Of course, it's weaker because spin-orbit coupling is weaker. And in fact, previously people thought that, in fact, 3D transition metal are not a good place to look for Kitaev physics. But there was some theoretical work originally by the group of Motome and later on by Khalilin and others who showed that indeed there could be Kitaev physics even in 3D transition metals. And motivated by that, other groups looked into honeycomb lattices in 3D made of cobalt 2+ or nickel 3+. An example of it is this system, barium cobalt arsenate. In this system, the blue atoms are the cobalt atoms. They form a honeycomb lattice. However, there is a bit of an issue in these systems. The issue is that you also have these arsenic oxygen 4 tetrahedra that are non-magnetic. It's completely non-magnetic, but it does form a bridge between different cobalt atoms or octahedral that contain a cobalt atom in them. And this bridging between the different cobalt octahedra could actually, turns out that it can mediate a nearest neighbor interaction. So you have a J1 and then you have a J3. And that J3 actually, next nearest interaction, seems to be pretty strong in these materials. And one reason for it is these bridges between the neighboring octahedra. And therefore, in fact, later on, more work has been done by the group of Arun Paramikanti in Toronto, who, among others, who showed that actually the better model to describe the physics of these systems may not be Kitaev model, it would be an XXZ model or a J1, J3 model. There has been also other work to show, basically to map a phase diagram for these systems, but I won't go into the details of it. I'll show you what was the contribution from our group. What we did, we knew that having this bridge is a problem because it creates this J3 term, which is strong. So we made a material that does not have that bridge. And the material is sodium cobalt tellurate. And this material has two polymorphs. One of it is hexagonal, the other one is monoclinic. We made both of them. But the monoclinic system is specifically sort of the same space group as the iridate and rhodates that I showed you. So it's really the ideal structure for these Kitaev materials. So we made this material, and it's kind of a clean honeycomb system. Other than having some sodium deficiency between the layers, there is no other disorder in the material. And in this system, we saw that it orders magnetically at 10 Kelvin, antiferromagnetically. We only made polycrystalline samples so far. We're trying to make single crystals, but so far we only have polycrystalline. So the system orders antiferromagnetically at 10 Kelvin. It has a Curie-wise temperature of 10 Kelvin, so you may think it's not frustrated because Curie-wise temperature and antiferromagnetic transition temperature are the same. But the important thing here is that the Curie-wise temperature is positive. It is ferromagnetic. But the transition itself is antiferromagnetic. So this tells us that the exchange coupling must be highly anisotropic, in fact, in this material. And that's why we want to make single crystals of it to look at the anisotropy of exchange interaction. Probably it has an antiferromagnetic coupling along maybe, I don't know, C-axis or A-axis, which is larger than 10 Kelvin. So we're trying to look for that. But we basically found what's the ordering in this system from neutron scattering, elastic neutron scattering. It's a zigzag order. And we also applied magnetic field to the system, and we saw that the order is kind of lifted, in fact, by increasing magnetic field. So these are kind of promising signs, actually, for magnetic. So basically by using an applied field, you can suppress the magnetic order in this material. Just like I showed you with pressure, you could suppress the transition temperature in silver lithium rhodate. Okay, I believe my time is up, and I'm not going to be able to go to the next topic, which is, I think, good timing. So I just leave it to this one topic. However, before ending my talk, I think I was a bit ambitious by putting too many slides, but let me at least go to the very last slide and just thank my group who did all the hard work. This is my group at Boston College. The students have done all this work. Faronak was our former student who was very active in this field. Lots of results were produced by her. Elena, also another student, worked in this work. And one of my new students was not in this picture. Shimi is also working on this physics. Some of the MuSR experiments that we did was with Piyush, whose picture is here. And so I would like to thank the students for their hard work. Thanks to the funding agencies, thanks to all the collaborators, and very much thanks to Alberto for his kind invitation, and Adrian also. And with that, I finish. Thank you for your attention.
I have a quick question.
Yes.
I should first open to.
Yes,
I forget I'm hosting this today, don't you? Are there questions from the audience?
Please.
Yes, go ahead.
I have a simple question. So the phase diagram, the lovely mosaic-looking circle, did I hear you correctly? Did you say that that was computed on some theoretical way? I was just wondering what method they were using to compute that phase diagram.
Oh, so the original, I think at least this one, right?
Yeah.
So I think the original ones were mostly like tight binding modeling of basically some kind of lattice and calculating the different couplings based on tight binding model.
Using some computational.
That's right, some computations.
Yeah.
So, but I haven't put some of the recent results. There are even machine learning algorithms that people are using to basically extend these calculations into 3D systems or 2D systems, or maybe even add more details about the coupling constants. Another line of calculations that have been also successful are quantum chemistry calculations. Those are done usually on clusters of molecules, not on a full not like on a large lattice, but small cluster of molecules or atoms. And those calculations are pretty good. They're maybe more accurate in terms of calculating the coupling constants, but they're much more difficult to kind of produce phase diagrams for.
In the tight binding approach,
Yeah.
do you remember what algorithm that was? Was it
I
DFT kind of thing, or?
Yeah, DFT based. But
Okay.
but if you want the details, I can give you the reference for this. Yeah, so that you can take a look.
If you Google Jeffrey Rao.
Yeah, Jeffrey Rao, this work particularly, I think, started 2014 PRD.
RAU.
Jeffrey Rao.
Yeah, but only happy to forward the reference.
Adrian, any questions? Any questions from the audience online? I have a question.
Something in chat, yes, please.
That's from the beginning.
Do you have crystals of the of the silver lithium product?
Unfortunately not,
No.
but it may be possible actually to make
Okay.
crystals. We're working on it, we don't have it now, but may be possible actually.
I'm very curious about has anyone done Raman spectroscopy?
No.
No.
No Raman spectroscopy.
In any of these materials? Maybe in the silver
in-
one.
Actually, we did on hydrogen
Right.
lithium
Silver.
mostly and the silver lithium
Yeah.
but that was basically just for structural.
Right. No, I'm very curious what happens or how the rotations might couple to the dumbbell molds.
Ah.
So I wonder if that's a way to dynamically control
Oh, I
the
see.
tilting of the object.
Absolutely. So I would say if there is a mode that could respond more
Yeah.
optically, could
Yeah,
be more
yeah, yeah.
comfortable, I would say is the dumbbell mode, especially.
Okay.
Because as much you can imagine, energetically speaking,
Yeah.
for example, if you look at lithium iridate, which has an octahedral of these oxygens around lithium,
Yeah.
it's a much more ionic bonding and much kind of more robust type of bonding, so there's less room for wiggles. But for something like silver, I
Right.
think those are more covalent bonds.
Right.
It's just easier, I would imagine,
I see.
to shake it basically.
Yeah, that could be interesting.
That
Actually.
would be interesting.
Yeah. If there are no other questions, we can thank Fazel for this great talk.
All right. Thank you, everybody.
Thank you, Fazel.